welcome back. We're looking at 8.2 Study Guide, the Pythagorean Theorem and its converse. We're going to look first at the Pythagorean Theorem, just a quick reminder of what it is. Here is a right triangle that we can use the Pythagorean Theorem on. What the Pythagorean Theorem tells us is that whenever we have a right triangle, we can add up the side lengths when we square them, and we take them and multiply them by themselves. And whatever we get when we do that and add them together, it's going to be equal to whatever we get when we take the hypotenuse and square it. It's written as this very lovely algebra equation right here, a squared plus b squared equals c squared. The only one that's super important for you to remember where it is and to put it in the right spot for your formula is the hypotenuse. The hypotenuse is always going to be c and will always be located directly across from your right angle. You must make sure that you put the hypotenuse information in C. Let's go ahead and do some examples. Number 1 asks us to find x. Let's identify where our hypotenuse is first. So here is our right angle, and hypotenuse is directly across from that. So in our equation of a squared plus b squared equals c squared, we must make sure that c squared is the hypotenuse. There is our equation. Remember that c squared must always be your hypotenuse, so I'm going to replace c squared with x. Everything else doesn't matter what order you put it in. So I can make one side be a, and the other side can be b, and everyone is happy. Let me fill in the rest of my equation. There it is. I'm going to go ahead and simplify this down. I have 3 squared, which is 9. 3 squared is 9. That equals x squared. 9 plus 9 is 18. And in order to get rid of a square power, you must take the square root. So the square root of 18 is the value of x. Now you can take this into your calculator and you can get a decimal, but let's go ahead and take a moment and actually reduce this radical. And for that, I need an extra sheet of paper to help me out. There is my extra sheet of paper. I'm going to look now at the square root of 18. I can think of 18 as the multiplication of two things, and one of which I want to be a perfect square, something I know the square root of. I know the square root of 9. The square root of 9 is 3. And so I can rewrite 18 as 9 times 2. Whenever you have a radical with a multiplication inside of it, you can break it up into two different radicals, and you can do that break right at the multiplication. So this first radical is going to have my first factor, the first thing I'm multiplying. And my second radical will have the second factor, the second thing I'm multiplying. The square root of 9 is 3, and since I don't have a good whole number square root for 2, I'm going to leave it alone, and so my final simplified answer is 3 square roots of 2. Let's look at number 2. I'm going to employ my extra sheet of paper already at the beginning so that I can just keep on writing. I need to identify my hypotenuse. I'm going to do that by finding my right angle. The side directly across from it is my hypotenuse. I'm going to assign the other sides to be A and B. Again, it doesn't matter which side you pick to be A and which side you pick to be B, so long as you make a choice. Here is my Pythagorean theorem. I'm going to go ahead and color code it for you this time so it's a little easier for you to see where I'm substituting in. All right, the measure of the side I selected as A is 9. The measure of the side I selected as B is X, that's my unknown. And the side I need to be my hypotenuse, C, is 15. And so my Pythagorean theorem looks like that. Beginning my simplification process, 9 squared is 81. X squared I'm going to leave alone, and 15 squared I'm going to go to my calculator again, because again I have a little trouble doing some of these multiplications in my head. My calculator shows it's 225. I'm going to subtract 81 from both sides because I'm trying to get x by itself. So subtracting 81 from both sides is going to remove 81 from this side. Back to my calculator. I know that I'm not displaying it. There it is. It's showing for me on my calculator that I'm using off screen is 144. I know the square root of 144 because my mama forced me to remember some of my squares, not all of them. Whoopsie. Taking the square root of both sides, the square root of 144 is 12. And so the answer to number 2 on your study guide is x equals 12. You continue along that same way for some of these others. Number 6 looks tricky just because the shape is interesting, but look closely and you can find your right triangle. Number 7, 8, and 9 require us to use Pythagorean triples. We have a table of Pythagorean triples. Those were available to you in class. If not, you can hit Google and find one to print out. All you need to do is confirm 2 of the 3 and the other side of that triple is right there. Just make sure that your hypotenuse is always the largest number. Some of them aren't going to have the numbers aren't going to show up in your set, and so what you need to do is you need to start reducing these numbers down a little bit. If I divide 28 by 2, I get 14, and if I divide 96 by 2, I get 48. Yes, I used my calculator to help me out. If the new set of numbers still doesn't appear, you're going to reduce it again by some factor that you can think of easily, and then you're going to check again. I happen to have this Pythagorean triple memorized. The Pythagorean triple is 7, 24, 25, but this is not the actual measure of the side. Remember, I got to these numbers by reducing, by dividing these numbers by something else. I divided by 2 to get to 48, and then by 2 again to 24, and so in total I divided by 4. If I want to undo that division, I need to do its opposite. To go from 24, I have to multiply by 4. And so to get to the actual side length of this triangle, I need to take this 25, which was my Pythagorean triple number, and multiply it by 4. That's how you work Pythagorean triples. Now on this one, we want to see if the triangles that we're displaying here, these are sets of sides, we want to know, are these sides triangles for acute triangles, obtuse triangles, or right triangles? And the only way to find that out is if we use the Pythagorean theorem in interesting ways. If we use the Pythagorean theorem and say that the measure of the two sides, the two short sides, squared and added together, equals the actual longest side, then that is a right triangle. But if when we do this addition, we realize that the two short sides squared and added together is bigger than the biggest side of our triangle, then the triangle is acute. We could also have the case where squaring the smaller sides and adding them together gives us a number that is smaller than the square of the largest side. When that happens, my triangle is obtuse. So I'm going to go ahead and come down here. We're going to look at number 4, and we're going to try this out. The biggest number is always going to be our C. The other two numbers, it doesn't matter what order you put them in. I like putting them in alphabetical order. And then I'm going to take my Pythagorean theorem. A squared plus B squared. But this time I'm not going to say C squared. This time I'm going to say that a squared plus b squared has some relationship that I don't know to c squared. Time to do some substitution. A is 6, b is 8. That result has some relationship to c squared. C is 9. All right, I'm going to do some simplification here. 6 squared is 6 times 6, or 36. 8 squared is 8 times 8, or 64. And that has some relationship to 9 squared. 9 times 9 is 81. 36 plus 64, again, I'm going to employ my calculator off to the side. That is 100. That has some relationship to 81. As I'm looking, I notice that a 100 is a bigger number than 81. According to my reference chart here at the top of my study guide, when that happens, the triangle is an acute triangle. And so, because I got this a squared plus b squared result larger than my c squared result, this triangle is an acute triangle. Let's try this again, but this time I want to look at it in terms of these values. These values have square roots, and already it looks very complicated, but it's the exact same sort of setup. We're going to select our numbers to be A, B, and C. And again, I like putting them in alphabetical order. I just need to make sure that the largest value of each one is going to be C, the biggest side of my triangle. And again, I'm going to employ a squared plus b squared. And again, I'm not going to know what the relationship is to the biggest side of this triangle, c squared, until I'm all done with my work. Now, a squared, now that it has a square root, I'm going to put parentheses around things. So here I am, I'm just opening some parentheses. A squared, a is square root of 5, b is square root of 12, and c is square root of 13. Now, as I look at this, I've got to keep in mind that square roots and square powers are inverses. They're opposites. They undo one another. And so since I have the square of a square root, the square and the square root kind of undo each other, and I'm left with just the 5. Repeat this process along all parts of this little statement here, and I end up with something that looks like this. 5 plus 12 is 17, and that has some relationship with 13. As I look at these numbers, I can tell that 17 is bigger than 13, and so this is an acute triangle. That's how you use Pythagorean Theorem as a device and a tool to help you decide what kind of triangle by angle measure, acute, right, or obtuse, you have in front of you. And this is your little cheat sheet chart that you should use to make that happen. Thanks so much for watching. We'll see you next time.